Well, hello everyone. This is KP, the Math G. Yeah, this is the shirt that I wear from time to time. Sometimes I don't wear it because, well, I have to wash it. Can't wear it all the time. So anyway, we have been doing some derivatives, and in this case, we just got off of implicit differentiation, and that's what we're going to use uh, when we're starting to find some related rates. This is one of my favorite um, topics to teach. Um, I don't know, I just like related rates. Now, let's begin with our first one. We're going to do two examples, one where the rate is increasing and one where the rate is decreasing. So in this case, I think the bubble or whatever we have here, the soap bubble, is going to be increasing. So let's read the question. It says how fast. Now underline that. How fast is the rate? Okay, whatever we're looking for, anytime we see how fast, that is going to be a rate. Dy over dt, dx over dt, dr over dt, dh over dt. In other words, if we have, for example, a height, or in this case maybe a radius, whatever it is, it would be dr with the radius with respect to time, dr over dt. So how fast does the radius, all right, we're looking at a radius, yes, the rate of change of a radius. So in this case right here, this little portion right here, we're looking at dr over dt. Okay, all right, it is a spherical soap bubble. Well, I hope soap bubbles are not flat. It's spherical. Okay. Just a sad joke from me. I'm bad at telling jokes. All right, it's a spherical, so we need to understand that there is a volume of a sphere. Okay, that's what we're looking at. All right, so how fast does the radius of a spherical soap bubble change? At the moment, the radius, so we know that the radius r, so r is at that moment that it is 1 centimeter. Okay, all right, air is blown into it. Okay, probably one of those little holes you dip it into a soap bubble thing, soaps, and then you blow through it. Okay, it says air is blown into it at a rate of 10 cubic centimeters per second. Anytime you see cubic centimeters, we're talking about volume. So we know that this is a rate right here, so we know that dV over dt is equal to 10 cubic centimeters per second. Okay, all right, so we are looking for this. That's what we're looking for. So let's look at the problem. We got to set it up first of all. I hope I have enough room for this problem. Okay, so let's see, V is equal to, all right, let's see, what's the volume of a sphere? You have to remember that. That's 4/3 pi r cubed. All right, one thing you have, I don't know that you're going to have these formulas given to you, so you're going to have to know what the volume of a sphere is, or whatever we're looking for. Now, we take the derivative. The derivative of the volume, or V, is actually 1, but we know that that's times dV over dt. And we already know what dv over dt is. Alright, now we're doing this. This is not the product rule. Pi is a number. So this is a number. This is a coefficient times, or a number times r cubed. Alright, so we're going to multiply. We're going to apply the power rule. So 3 times 4/3 pi r squared. Now remember, at the end of the r, whatever you find a derivative of in this particular case, you're going to put in this case, dv over dt. Over here, you're going to put dr over dt. Alright, so every time you find a derivative of any variable, you're going to put that letter dr or dv over dt at the end of it. Alright, so let's see. We did this correctly, I do believe. 3 times 4/3 pi r squared. We got to subtract 1 from 3 to get 2 there. Alright, so here we go. Let's look at this. 1 times dv over dt is dv over dt. Alright, that's equal to, now look at this. This is 3 over 1. This divides out. So we're left with 4 pi r squared dr over dt. Okay, there it is. Now, let's plug in numbers so that we can figure this out. We said that dv over dt, that's the rate of the volume. Okay, the volume is increasing at a rate of 10 cubic centimeters per second. So in this case right here, that's where that's going to go. Let's put it right here. Let's just put the numbers down first. Alright, so now that's equal to 4 times pi. Now r, well, let's see. We already know what r is. That's 1 centimeter. So times 1 times dr over dt. That's what says how fast does the radius change. Okay, so let's see. That would be dr over dt, and that's what we're looking for here. We have all the numbers plugged in, and don't ever plug the numbers in until you find the derivative first. That is very, very important to understand that. Well, let's see. Let's solve for dr over dt. We're going to say 10. Now 4 times 1 is 4, so we're just going to divide by 4 pi. 4 pi, and that's equal to dr over dt. And dr rate is in terms of centimeters, never cubic or square. It is in centimeters per second. And we have to reduce this. 10 over 4 is 5 over 2. So 5 over 2 pi, and then that is going to be centimeters per second. You want to do that. Now that's equal to dr over dt. And that is the answer. Okay, that's what we're looking for. We're looking for how fast does the radius, dr over dt. Okay. And I know that we could have done some preliminary problem to understand that this is dr. We could have looked at this one. This air is blown in at a rate. Alright, you see that word rate right there? That's the same thing. How fast is some rate right here? Alright, so rate is always something over dt. Alright, d something over dt. So this is that. First of all, you have to set up the problem. You have to know that formula. Okay. Alright, and then from there take the derivative. That's pretty good. Pretty good problem right there. Okay. On the other side, we have one very common problem here. Yeah. You know, if I lose a little bit of this weight right here, I might not have to worry about stepping back so I can flip this thing over. Now, I do lift weights, but I do need to lose this weight too. Okay, gain weights in my arms and my legs. I just need to lose weight in my belly. Enough of that. All right, here's a ladder, and this is a very common problem. A ladder problem, leaning up against a wall, and I imagine it's going to look like this. You're going to have a vertical wall, and you're going to have a horizontal ground here, so that we can form a right triangle. That's the idea. All right, here's the ladder. All right, we already know we're going to look at that ladder. The ladder is, we'll call this maybe Z. Okay, so Z is equal to 26 feet. All right, we already know that. All right, what is happening here? All right, so we call this, we're going to look at this in just a moment, this whole problem in just a moment. But the height is usually Y, the horizontal is usually X. Associated with Y, of course, is going to be not equal to, but the rate of Y would be dy over dt. The rate of X is dx over dt. Like that, okay? All right. If the ladder, since the ladder is a constant length, the rate of that, dz over dt, since this ladder is not going to change its length at all, not going to shrink down any at a certain rate, so we'll find that that rate is equal to 0. We really don't need that, but in case you want to be a little particular about this, a rate is something is moving, something's happening. Let's read this little problem here. A ladder 26 feet long rests on a horizontal ground, all right, there it is, and leans on a vertical wall, there it is. The foot of the ladder is pulled away, so this foot of this ladder is being pulled away this way. In other words, X is going to get longer, isn't it? As you pull this ladder away, X, let's get a different color. Okay, let's just use this one right here. Alright, this ladder is going down this way at a certain rate, and it's going this way at a certain rate. And those rates are not the same, by the way. Okay, so let's see. This ladder is moving in the x direction. That would be at a rate. The rate is dx over dt of 4. So we know that this is 4 feet per second. It's moving in the x direction at 4 feet per second. Alright, so we know that it's moving away this way. X is changing, so what's happening is this ladder is gradually, or maybe fast, going down. This same 26-foot ladder is now the X value. The X is going outward while the Y value is getting shorter and shorter. It starts off this high, but now Y is now this high. So it's going down, all right? So the rate is going downward, okay? All right, so that's what we're looking at here. All right, it leans on a vertical wall. The foot of the ladder is being pulled away at a rate of 4 feet per second. How fast? All right, that's a rate. How fast is something? How fast is the top of the ladder? All right, so let's do that. How fast is the top of the ladder sliding down? The top of the ladder is sliding down the y wall, isn't it? Okay, you see what I'm talking about? I should face the camera every once in a while. I had a professor looking at the board the whole time, and I never did learn a whole lot. I did, okay, but it's kind of awkward, okay, doing that all the time. Alright, so how fast is the top of the ladder sliding down? This is a rate right here, okay. The top of the ladder is sliding down, so how fast is this happening here? How fast is y changing? Alright, we know how fast x is changing. Dx over dt is 4 feet per second. Alright, we know how fast that's changing. How fast is y changing? You might say, well, that's 4 feet per second also. Well, that's not so. Okay, we're going to find that that is not so. Alright, so when the foot of the ladder is 10 feet, so at a point, at the moment, that the foot of the ladder is 10 feet from the wall. So we know that eventually the ladder does reach 10 feet from, okay, like that. The ladder is 10 feet from the wall. So that's x. The x value at that moment is 10 feet. Okay? So here we have it. We have a triangle, don't we? Do we not have a Pythagorean formula for that? So we have x squared plus y squared is equal to z squared. Alright, so we know right now how long the x is for right now. So I said go ahead and do the derivative before plugging in any numbers. So we're going to go by that. We could, the only thing is we don't know how high y is, and we can figure that out. Okay, and actually that's what we should do. We should figure this out, and we could solve for y and figure out, well, how high is y at that moment. Alright, so let's go ahead and let's see how we can approach this. It would be nice if we could figure out how far y is, but we're going to go ahead and do the derivative like I said. Alright, so here we go. 2x times dx over dt. Notice there's x, so dx over dt plus 2y times dy over dt is equal to 2z times dz over dt. Okay. One thing we could do, we could divide each side by 2, or every term by 2. Alright, we would do that. I didn't do it this way in the problem, so see how it works. I think it's going to be okay. So x dx over dt plus y dy over dt is equal to z dz over dt. Alright, I believe at this point we can start plugging some numbers in and we can figure this thing out. So we're going to have two things that we don't know. We're not going to know y, and we don't know the rate that this is going down. That's really what we're looking for, but we can find out what y is in just a moment. Okay, we may need to erase our figure here. We might can get away without it, but let's go ahead and plug in some numbers. Once we've found this derivative, we can plug in some numbers. We know that x at the moment, this is a freeze frame is what we're looking at. At that moment, alright, x is 10 feet. Alright, I'm not going to put the units in just yet. dx over dt, since x is increasing, this is going to be a positive number right here, not negative. Alright, x is increasing at a rate, so we're going to keep the positive, so times 4. Alright, now we just need to find y, and we have to really find dy over dt. but we will find y shortly. Z is 26 feet long, and dz over dt, that has to do with the ladder. The ladder is still staying, if you will, rigid. It's staying the same 26 feet, whether it is up here or whether it's on down here. So that does not change at all. And if the rate does not change, then that is equal to 0. The rate is 0. It's kind of like this, and in one of my problems, if you find a right circular cylinder right here, the rate that water, if you have a rate here and you have R, and then you talk about dr over dt, well, if the water is going down or filling up, the rate is of the radius does not change because the radius is the same throughout, and in this particular case that also is 0. So there are times when the rate of that radius does not change. If this were, and I don't mean to get off to a different problem, but if that's a cone, we have a different problem because the radius does change. The radius does get smaller and smaller and smaller if the water level is going down, or even if it's rising up, it's getting larger and larger and larger. So there are times when the rate has to change. And where's my eraser, which I do not see? Hold on just a minute. It's probably on the other side, and it is. Let's get it. Okay, let's erase this part right here. We do not need that. Alright, so what we have here is 40. Okay, I'm probably going to have to erase this also. Oh, I hate that because, well, it does give you a good picture of this. Let's see if we can put it over here on the side. My magnet is not working properly, and I did lose one of the magnets. Okay, well, alright. I have 2 magnets here. Alright, let's see if we can squeeze it in. Squeeze it in here. Alright, so 10 times 4 is 40 plus y dy over dt is equal to 0. All of this now is 0. Alright, so let's see what we get here. Okay, so I need to find out what y is. I still have x squared plus y squared is z squared. Alright, so let's see, x squared, remember at the moment that this is 10 feet, so x squared plus y squared is equal to z squared. We know at that moment that 10 squared plus y squared is, the ladder is never going to change. That's 26 squared. And let's look at the numbers. We know that 10 squared is 100. Alright, so 100 plus y squared is 26 squared, which I believe is 576. I think. Let's see. 25 times 25. 25 squared is 625. I want to say maybe it's 676. I think. Okay. Alright, and then if we subtract 100 over here, plus y squared, well, if we subtract 100 on both sides, oh my goodness, minus 100. Alright, so y squared is 576, and you know how to solve for something that's squared. You just simply take the square root of both sides, and the square root of 576 is, now we could say plus or minus 24, but since the length is not negative, we're going to take the positive answer. So positive 24, I think we are having units in terms of feet, so 24 feet. So in this case now we know that y is 24 feet. Let's erase this part here. Alright, so we know y is 24. So y is 24 feet. Alright. And we are looking at this at the instant that the x, or the bottom of the ladder, goes up 10 feet from the wall. Okay. Okay. Here we are right here. I think this is it. Alright, so now we have 40 plus 24. dy over dt is equal to 0. Now we can subtract 40 on both sides. And if we do that, we're going to have 24 dy over dt is going to be a negative number, and it should be for obvious reasons, which we're going to look at in just a moment. Now, divide both sides by 24. This is a good problem, isn't it? Because we had to find both y and dy over dt. Alright, so that's the difference in our problem. Dy over dt is equal to, alright, let's see, 8 times 5 is 40, but that's a negative 5, and 24, 8 into 24 is 3, so 5/3, or negative 5/3, let's see, feet per second. Now if you leave it like this, this is fine. But here is a problem that we need to pay very close attention to when you're writing an answer down. Okay, especially when something is decreasing at a rate. And of course y is certainly decreasing because it started off up here and now it's sliding down the wall, isn't it? Okay, so let's see here. Let's put our problem down. If you want to say something, be very, very careful how you answer this. Alright, so what we can say here is that y, or well, let's see, the top of the ladder is decreasing already decreasing, so there's your negative sign right there, at a rate of, and then we say 5/3 feet per second. The no-no on this is to say it's decreasing or going down. If you say it's decreasing, then you put that's actually going back up, because a negative times a negative is a positive. You cannot do that. Okay, you cannot put the negative there. You must say positive here. This is the negative sign right here. It is decreasing at a rate. Alright, it's going down at a rate. Alright, so down is negative. Now if you said increasing, or can't be increasing, well, if you say increasing, which would be really crazy to say that, but alright, if you said increasing, it's going in a negative direction, that would be crazy to say that. You have to say it's going in a negative direction. So really, when you say decreasing, or going down, then the negative sign does not need to be there. I think sometimes if you just left it right here, but I think they would like an explanation. What did you find? You found this, but what did you find? And you have to be able to explain what you just found. You found that the top of the ladder is going down at a rate of 5 over 3 feet per second. So sometimes you need to finish off the problem to get the full points. Okay. All right, well that is what we have done. In our first problem, actually let's just look at this one first. We found that this y is decreasing. Now sometimes we're asked to find how fast is the bottom of the ladder, how fast is the bottom of the ladder increasing, okay? So sometimes we may not have this, but we know this answer. We're told what this is, and notice that it's not equal to the same thing. This is 4 feet per second, this is under 4 feet per second. Matter of fact, it's a little bit over 1 foot per second. Okay, okay, so that's what I'm referring to here. All right, so that's what we're talking about here. You needed to know on the ladder, x squared plus y squared equals z squared. Okay, you need to know how to find y, or in this case y, and dy over dt. All right, so at that moment here, okay, that's what you have to understand. It is at that moment. All right, from the last problem here, all right, we did not have a negative answer simply because the radius is getting, or